Welcome to our second video dealing with oscilloscopes. In the previous video, we have covered the very basics of scopes, and now we're going to talk about some of the most important features that modern scopes offer. Furthermore, we're going to discuss how to set up a measurement configuration and what things we need to pay attention to. So let us start with exploring our scope. Last time, we have simply connected our signal generator to the input of our scope. In general, these inputs have an impedance of about 1 mega ohm and are therefore high ohmic, such as voltmeters. Some scopes also offer the possibility to change to a 50 ohm input for high-speed signals. Until now, we have neglected any parasitics that might come from the scope input itself. For this case, probes can be useful as they allow to adjust to the measurement's needs. There are multiple types of probes like passive, active, differential, and many more. Let us start with the most common type, which are passive probes. These are used for general purpose measurements and only consist of passive components such as resistors or capacitances. They can propagate the signal without attenuation or with attenuation factors of usually 10, 100 or 1000 to the scope input. As an example, let us have a look at this 10-to-1 probe that I'm holding in my hand. A typical schematic of such a probe could look like this. We can see the scope channel input impedance, a compensation capacitance, and a probe input impedance. You can see that the 9 mega ohm resistor of the probe and the 1 mega ohm resistor of the scope act as a voltage divider of 10-to-1 for DC. The voltage probe offers a compensation capacitor which needs to be adjusted accordingly so that this ratio of 10-to-1 is maintained over a broader frequency range. Depending on the scope and the probe, this ratio of 10-to-1 is either set automatically by the scope or has to be changed manually in a channel menu. A simple way to calibrate this compensation capacitor is to use the scope and the rectangular signal. In this case, we will use the demo signal that is already provided by most scopes. We can see that the rectangular signal does not appear to be rectangular. Therefore, the compensation capacitance has to be adjusted by using a screwdriver until a rectangular signal is visible. Besides passive probes, there are active probes that use active components such as transistors or amplifiers. They have an increased input resistance and a decreased input capacitance and can therefore be used for high impedance circuits and also for high-speed measurements. A drawback is introduced by their limited input voltage range. A third type of probes are differential probes. Usually, a scope measures a voltage between a node in a circuit and common ground. In contrary to normal probes, differential probes allow to measure voltages between two arbitrary points in a circuit, which has quite some advantages, as we will see shortly. Differential probes can especially be used for signals of low amplitude and provide a very good common mode rejection. The difference between the two input signals is the input of a differential amplifier. It is providing a single-ended output signal that is passed on to the single-ended scope input. Before we start our measurements, a few words have to be said about the test setup in general. We have to take specific care as usually the ground potentials of both, so scope and power supply, are the same and connected together via the power grid. In contrast to a handheld multimeter, which is isolated, the reference potentials of a scope must not be set to any arbitrary potential in general. To emphasize this problem, we investigate this simple test setup. It only consists of a voltage divider circuit, the signal generator, and the scope with its probe. When measuring the voltage over R1, the probe ground and therefore the scope ground and also the signal generator ground are on the same potential, and therefore this measurement poses no problem. However, when trying to measure the voltage over R2, the resistor R1 is shorted over the power grid. Consequently, there is no voltage drop over the resistor, as both nets are on ground potential, and therefore R1 will have no effect on the circuit. In other words, we have changed the behavior of our circuit with our measurement. In order to still be able to measure the voltage over R2, different approaches are possible. One possibility would be to use two channels, measuring the voltages with reference to ground and subtracting one channel from the other. In order to do this, most scopes offer a math menu, where you can do a simple subtraction of the voltages. We will show an example for this function later in the video. Another possibility would be to isolate either the power supply or the scope by an isolation transformer, so that the grounds are not connected together. However, most scope manuals suggest to float the power supply and not the scope, as of accuracy reasons. Last but not least, as we have already mentioned before, also a differential probe could be used. In our previous video, we have already seen the usual plotting mode of a scope, which is voltage over time. However, there is a second option, which is called XY mode. In this mode, one signal is plotted with respect to the other signal. In our example, channel 1 will represent the x-axis, whereas channel 2 is the y-axis. Let us again look at a simple example. The signal on the first channel is a ramp, whereas the second one is a sinus. We can also verify this on the scope. Now that we have verified that there are some reasonable signals on the channels, we can change the time mode in horizontal menu to XY. The outcome is exactly one period of a sinus. Let us find out why we see this result. Let us therefore have a look at the animation. For every point in time, the values of channel 1 and channel 2 are mapped to a point in the XY domain. When this is done over a longer time, the points form the given curve. In this case, the sinusoidal signal is simply projected as is by the linear ramp signal. Using the XY mode, we can also make hysteresis visible. In this exercise, we will use an inverting Schmidt trigger and put a triangle signal on its input. This triangle signal is our X input. The Y input is the output of the inverting Schmidt trigger. This gives the expected hysteresis curve. We have to admit that we cheated a little bit for this example, as we have added a capacitor so that the edges become more visible. However, in this example we could not know into which direction the curve is oriented, if we would not know the schematic behind it. In order to get this information, an easy trick is to lower the input signal's frequency until the signal course is also visible to our eyes. In this case, we could set it to a frequency of 1 Hz. By doing so, we only see a single dot that is moving over the screen. But we can highlight its trace by setting the scope screen's persistence to an appropriate time. This is done by pressing the display button and turning the persistence on. Now we can see both the hysteresis curve and its direction. The persistence itself was first a feature of analog scopes that has been adapted to most digital scopes by software. Let us finish XY mode with a little brain teaser. We have the following schematic where base and collector are driven by independent voltage sources. The current is measured via the voltage over a small shunt resistance R that is neglected for the collector-emitter voltage measurement. Using the collector-emitter voltage as X and the current-dependent voltage over R as Y input, we can produce the following curve. Now the question arises, How do the applied voltage signals look like in order to get this result? In the last video, we have learned about triggers that capture a periodic signal. But what should we do if the signal we want to capture does only occur once at a random point in time? An example is observing the contact bouncing or chattering when using mechanical switches. Have a look at our test setup. We have a switch that is connecting a resistor to a voltage source. We can observe the voltage on a node between the switch and the resistor. The trigger itself is set to rising edge. Let us now flip the switch. We see that the switching process is not captured. Therefore, we have to push the single shot button. As the name implies, this only performs a single capture at the first trigger event and keeps the data so that it can be observed. We can see the contact bounce as we have expected it to be. If we want to observe another switching event, we have to enable the next shot by pressing the single shot button again. As we have mentioned before, we can use math functions to measure differential voltages between two arbitrary points in a circuit. For this approach, we need a difference math function. In this way, we get a proper resistor voltage over time. However, there are also other mathematical operations available. To give an example, we subtract a triangular from a rectangular signal. Therefore, we go to the Math menu and select the difference function. Depending on the scope capabilities, there are even more complex functions possible, such as fast Fourier transforms or FFTs. Applying the FFT to a rectangular signal will give us a sinc function. You can see the main frequency and the odd harmonics. Another nice feature of modern scopes are the so-called measure functions. Obviously, they can be used to measure different signal characteristics, such as peak-to-peak voltages, root mean square voltages, periods and frequencies, and many more. Let us continue with another example. We use a bipolar transistor differential amplifier and would like to measure the differential gain. Therefore, we set a negative input to ground and apply a small sinusoidal signal on a positive input. We can see some problems with our measurement. The input signal is very noisy and some noise peaks are triggering the signal recording. In order to reduce this effect, we can go to mode coupling and we could select HF reject. In this way, a low-pass filter with a corner frequency of about 50 kHz is added to the trigger path. In this way, the trigger is not influenced by high-frequency noise anymore. Another possibility would be to use an external trigger, where an additional trigger signal is created and passed on to the scope. Both our signal generator and the scope offer an external trigger board on the back side. On the signal generator, it is called sync out and it has to be enabled in the utility menu. On the scope, it's called external trigger in, and of course the trigger has to be set to external. In order to add the measurements, we can go to the Measure menu, select the first channel, select our type of measurement, which is peak-to-peak, of course, and we can add the measurement to the side panel. In the same way, we can also do it for the second channel, again selecting the measurement and adding it. And now, as we have both the peak-to-peak voltages of the input and the output, we can calculate our differential gain. However, you can see that due to the noise on channel 1, the measurements are quite inaccurate. To reduce this effect, we can average our signal over some periods, which gives us a noise-free signal. In this way, our amplitude measurement becomes quite more accurate. To do so, we have to go to the Acquire menu and select Averaging in the Acquire mode. A manual way of measuring characteristics of a waveform is also available when using so-called cursors. Again, there are different modes available in the cursor menu. From a fully manual cursor mode, where X and Y axis have to be defined separately, to a tracking mode, where only the X axis is defined and the Y axis is obtained from the signal. This completes our overview of some of the most commonly available functions of modern oscilloscopes. We have covered important features that scopes offer. Handling such a complex measurement device may seem a little bit tricky at first, but you will get used to the most significant features simply by trial and error. Of course, this is not everything. For sure, you will find even more features on this and also on other scopes. Feel free to comment on the video or tell us if you think that we missed something important. I'm Dominic with the Institute of Electronics. We hope you have learned something today. But anyway, thanks for watching.